Welcome to the 24th lecture in this beginner's course on algebraic topology. I'm N J Wildberger at the University of New South Wales, and today we're going to introduce the fundamental group of a surface. So it's a very important link between the topology and the algebra. So let's suppose we have a surface. Let's call it M. And it might be a torus with a couple of holes like that, or maybe we can imagine having a few extra handles. We can draw also like that, or maybe there's a cross cap on it, which we can kind of draw loosely like this, something like that. And what we're going to be talking about here is paths or loops on the surface. So we start with our standard interval, which we just assume it's the standard unit interval from 0 to 1 on the line, and let's call that I. And we're going to be looking at maps or functions from this interval into our surface. So the image of such a map will be a path in the surface. So there, let's call the function alpha. So at this point here, that would be alpha of 0. And this endpoint, alpha of 1. And as t goes from 0 to 1, alpha of t goes from this point to that point. It's a path on the surface. So a path in M, by that we mean a function from the standard interval into our surface. And it's got to be continuous. A continuous function. And the point alpha 0 is called the initial point. And the point alpha of 1 is called the end point, or final point, let's say. And both of these are what we might call end points of the path. And a special case is when the initial point and the final point agree. So if alpha of 0 equals alpha of 1, that means the path closes on itself. Then we call the path is a loop. That would be like this, perhaps. And the actual image of the path can wander around wherever it wants to. It's not constrained. It can cross itself. It can repeat itself. It can do whatever it wants. It can go around holes, just as it likes. Now, of course, there are many paths on a surface. In some sense, there are too many of them to consider them all separately. So what we want to do is we want to group paths which are essentially the same together. And the notion of essentially the same in this context is the notion of homotopic. So that's our next business. What do we mean by homotopic paths? So our picture is we have our surface. And let's say we have one path, let's say alpha, and another path, beta, with the same initial and final points. So we say two paths, alpha and beta, with common endpoints. In other words, alpha of 0 equals beta of 0, and alpha of 1 equals beta of 1. Two such paths are equivalent or homotopic precisely when there exists a map H from the interval cross the interval into our surface. Continuous. Continuous function with the property or such that h of t0 equals alpha of t for t in 0, 1. H of t comma 1 equals beta of t for t in 0, 1. And h of 0s equals alpha of 0 for s in 0, 1. And h of 1s equals alpha of 1, also for s in 0, 1. And alpha of 0 is the same as beta of 0, so we can also put beta of 0 there. We can also put beta of 1 there. And the picture is in terms of a square. This is a picture of the interval cross the interval, which is a square. And the usual agreement is that we consider the first entry to be, say, t, and the second entry s. So that number t is going from 0 to 1, and this number s is also going from 0 to 1. And we require the following. So what's the meaning of these conditions? The meaning is that if we set the second coordinate equal to 0, so that means we're traversing along this path. So if we go along this path here, from t equals 0 to 1, then the image of this map, the image over here, is exactly the curve alpha. And if we traverse this particular path, when the second coordinate is equal to 1, then we're traversing the curve beta. We're going along here. And so these intermediate horizontal lines, their images are going to form a family of curves that go smoothly and continuously from the alpha curve all the way up to the beta curve. And the meaning of these conditions here simply is that all of these points are getting sent to that initial point, that common initial point, and that all of these points here are being sent to the final point. So all of these curves, as we go across from here to here, all of these curves will have the property that they start here and they end here. And you can think of this as being like a movie. A movie going from the alpha curve to the beta curve continuously. So we can continuously deform alpha to beta. And that's the meaning of what it means for alpha and beta to be homotopic. And in algebraic topology, we often consider two curves which are homotopic like this to be essentially the same, because we like to deform things continuously and say that things are not mattering. So as long as we keep our endpoints fixed, we can push the curve around and it'll still be homotopic to what it started with. So essentially then H is giving us a family of curves or paths connecting alpha and beta. And how do we represent this notion of homotopic or equivalence? We represent with this symbol here. We'll write alpha tilde beta. So that's going to be our notation for alpha and beta being homotopic or equivalent. All right, so the first fact is proposition. Homotopy is an equivalence relation. I'll have to explain what that means. So what does that mean? It means that any curve is homotopic to itself. It means that if alpha is homotopic to beta, then beta is homotopic to alpha. And the third condition for an equivalence relation is that if alpha is homotopic to beta and beta is homotopic to gamma, we have three curves, then there's a transitivity, then alpha is homotopic to gamma. So you can take that to be the definition of what we mean by an equivalence relation. Those three properties are exactly the properties of an equivalence relation. We want to show that this notion of homotopy satisfies those. Okay, now I'm going to sort of show this by pictures in terms of diagrams like this. Sometimes I'll write down some formulas, but maybe a little bit later I'll dispense with the formulas. Let's start. The proof of the first one. Why is any curve homotopic to itself? Well, let's draw it like this. So we need to put our surface here. We have a path alpha. So here is the interval I cross I. We have to define a continuous map H, which goes from the curve alpha down here to the curve alpha up there. And the obvious way to do that is simply to make this function constant on these vertical lines. So we define h of t and s to be, by definition, alpha of t. Then this defines a map from I cross I into the surface. And when s is 0, we get alpha of t. When s is 1, we get alpha of t. In fact, for any value of s, we get alpha of t. So as we go up along here and look at the successive images of these lines, we're always getting the same curve. It's almost trivial, really. All right, our second part. We have to show that if alpha is homotopic to beta, then beta is homotopic to alpha. So suppose we have a homotopy, let's just call it H, from the usual I cross I, going from alpha to beta. Okay? This is going to be some map into some surface M. So that's a homotopy showing that alpha is homotopy to beta. And we want to cook up another homotopy from beta to alpha. Let's call this new homotopy H tilde. Then what we should do is we should define H tilde of TS to be just this homotopy flipped around so that the alpha and the beta interchange. And how do we flip that around? We replace the S with 1 minus S. So that can be a definition of the homotopy H tilde. And then that is going to have the property that when you start down here, you're getting beta. And when you arrive up there, you're getting alpha. So that's a homotopy then from beta to alpha. Okay, and the third property, let's suppose that if alpha is homotopic to beta and beta is homotopic to gamma. So what does that mean? Okay, so there's one path, it's called alpha, and there's a homotopic path beta, and here is a homotopic path gamma. Okay. So what we can assume is that we have actual homotopies, these H's. So we have homotopy H from alpha to beta. Okay, and this is actually a continuous map into here, which sends this bottom to alpha and this top to beta. And we also assume that we have another homotopy. Let's call it K over here. A homotopy from beta to gamma. So that would be sort of beta on the bottom and gamma on the top. So we also have such a map. Let's call it K. And what do we want? We want to prove that alpha is homotopic to gamma. And what does that mean? Well, that means that we have to cook up a new homotopy, let's call it L, that starts at the bottom with alpha and ends at the top with gamma. And so what we do is we combine these two homotopies judiciously. And how do we do that? Well, we sort of just slice this at the halfway point, going from 0 to 1, so that would be the halfway point, a half there. And we'll put H down here and K here, diagrammatically. Okay, well, we do have to squish a little bit because this is actually going from 0 to 1, so we're going to have to sort of squish H down, and we're going to have to squish K up so that they fit together. And intermediate then, in that middle part, that's going to be where beta is going to be. Okay, and how do we write that in terms of formula? So here's the formula. We say that L of T and S equals two possibilities. H of T2S for S between 0 and a half. That's effectively squishing H down. So as S goes from 0 to a half, this goes through the whole range of H. And the other one, it will be H of T and 2S minus 1 for S in the other range from between a half and 1. And that's taking, not H, that was H, K over here. That's taking K and essentially shifting it to this range here. So that's how we create a homotopy then from alpha to gamma. That's what we wanted. All right, so we already said that a loop is a path alpha with alpha 0 equals alpha 1. And that might be called the base point of the loop. It starts and ends at the same point. And there's a very special case of this, which is very simple. So, simple but important special case. It's called the constant loop. And it is just a path which has the property that alpha of t is equal to alpha 0 for all t in our interval. This is a path that is not going anywhere. So now we're going to describe how to multiply paths. All right, so if we have two paths which are related in an important way. So if alpha and beta are paths in M is a fixed surface with the property that alpha of 1 equals beta of 0. So there's our path alpha, and then there's our path beta. Then we're going to define a new path. Then define the product path alpha times beta in the following way, that alpha times beta at t is, all right, alpha of 2t if t is between 0.5, and beta of 2t minus 1 if t is between 1/2 and 1. So this is a new path that's going twice as fast over the alpha part. It doesn't take 1 to get there. It goes there in 1/2. And then it goes twice as fast along the beta part. So still in the interval 0 to 1, it manages to go across that entire combined path. And we call that the product of the paths. All right, so lemma. That means little result. So if alpha is homotopic to alpha prime and beta is homotopic to beta prime, then alpha times beta is homotopic to alpha prime times beta prime. So for example, suppose that's alpha, and suppose here is alpha prime, which is homotopic to it. And suppose that beta is such that it starts where alpha left off. And here is beta prime, which is homotopic to it. Then we want to show that the combined path alpha times beta, there it is right there, is homotopic to the combined path alpha prime times beta prime. All right, I'll draw you the picture and I'll leave you the details. So here's the idea, that we have a homotopy from alpha to alpha prime. All right, let's call it H. So we have such a homotopy. That's just encoding this movement from here to here. And we have another homotopy from beta to beta prime. Let's call it K. That's encoding the movement from beta to beta prime. So what do we do then? Well, we're going to put them together, but in kind of the opposite way we put them together last time. Now we're going to put H on this side and K on this side. And then that's going to be a homotopy from here's alpha followed by beta down here. And here's alpha prime followed by beta prime up here. We just have to kind of go in this direction twice as fast to cram this into this half interval here, and go this twice as fast to cram it into that interval there. And then that's going to be a homotopy from alpha times beta to alpha prime times beta prime. So the details left to you. You can write down formulas if you like. Okay, so that means that we can think of this multiplication actually on not the paths themselves, but the paths with a kind of an equivalence of this homotopy. And the standard way in which that's done is by introducing the idea of an equivalence class. All right. So we write the equivalence class of a path alpha. Now, strictly speaking, this usually involves some abstract set theory that I do not approve of, because equivalence classes invoke all kinds of infinite objects, which I find unacceptable. But anyway, the standard thing is to define an equivalence class like this as the set of all paths which are homotopic to alpha. Okay, to me that's incomprehensible to understand. But so I still want to talk about something like that. Okay, so I prefer to just think, perhaps, I'll still use this symbol, but if you want to be a little bit more honest, you might think of this as an equivalence type. In other words, you can just regard this as an expression, as a symbol, okay, with the agreement, it's just a symbol, with the agreement that alpha equals beta if alpha is homotopic to beta. And we have a very clear way of deciding whether two things are homotopic. So we don't have to invoke infinities, so we can just talk about a symbol associated to a path. And we'll still call it the equivalence class, because I don't want to depart too much, but you could also call it an equivalence type. And so now the consequence of this lemma is that multiplication is well defined on equivalence classes or on equivalence types. It's well defined on equivalence classes or types. In other words, that we can say, all right, if we have a path alpha, and that's its equivalence path, equivalence type or equivalence class, and then that times the equivalence class of beta is by definition the equivalence class of alpha times beta. And if you substitute alpha for something homotopic to it, and substitute beta with something that's homotopic to it, you're going to get something over here which is homotopic to this one. So still in the same class. So that means it's well defined on the classes. An important special case of all this is when we're talking about loops. So a special case. Suppose that we have a fixed point, x0 is a point on our surface M. So we fixed a point x0. And now we can consider just paths which start and end at x0. So loops based at x0. Then the equivalence classes or types of loops based at x0 will automatically multiply with each other, because one will automatically start where the last one stopped. So given any two loops, we can multiply them and we'll get another loop based at x0. So that means we have a closed system. We don't have to worry about the first one ending where the second one began. So it means we can multiply any two such equivalent types. And that gives us an algebraic object. An algebraic object, which is called, denoted usually pi of M. And just to put its dependence on x0, we'll put an x0 there. And it's called the fundamental group. The fundamental group of M. Okay, based at x0. we'll shortly see that the x0 is actually not that important. It's the m that's important. All right, so let's have a look at some examples. All right, so example. Suppose that M happens to be a polygon, which is topologically the same as a disk. Okay, so there's M. We're talking about this. It's a surface with boundary. And we've chosen some point x0 inside it. And we're looking at loops based at this point x0. They start and end at x0, yes. Well, the main fact is that all loops at x0 are null homotopic. Now that's a fancy word for, i.e., they are homotopic to the constant loop at x0. In other words, the loop that stays where it is through the entire movie. Doesn't go anywhere. And why is that? Well, how could you make a movie that continuously deforms this loop to the constant loop? That's what a homotopy is. It's a kind of a sequence of slides, picture that goes from this to the constant loop. Well, what you can do is you can just use the fact that this is kind of star-shaped, that you can see every point from x0. And you can imagine like a spider. This is like a spider at x0, just drawing in on its web everything. So imagine just bringing everything into x0 at a constant rate. So starting here and then shrinking in. So what would happen to this loop as we did that? Well, everything would be just being pulled in. So a little while later it would look like, I guess it would look like that. And then a little while later it would look like that. And a little while later it would look like that. And when t was equal to 1, it would be back to the constant loop. So that's a homotopy from any loop, in fact, to the constant loop. It doesn't matter what the loop does, because this shrinkage affects the entire space and allows you to shrink the entire space to the point. So everything is going to be caught by that movie and shrunk to x0. And that means that there's really only one element in this group. So pi of m, or pi of the disk, or pi of the polygon, only has one element. Okay, we might call that element, say, alpha 0. Let that be a name for the constant loop. For our second example, we're going to go back to something that we've already talked about, the case when our space is our circle. Okay. So here's our circle. And let's give it some pleasant coordinates. Let's call that 0 equals 0 and 1/4 and a half and 3/4. So we'll just use the sort of natural turn coordinates. So it's parameterized from 0 to 1, which is, of course, much better than 0 to pi, isn't it? Or 0 to 2 pi. Much more natural. Okay, so now how can we describe some loops in this situation? Well, first of all, there's alpha of 0, which is the constant loop. And our base point, natural to take, say, this point here as our base point. That doesn't really matter. And then we have some other loops. Well, we could define alpha 1, say. And we could define alpha 1 by defining alpha 1 of t to be t. As t ranges from 0 to 1, that means we're just going around once. So that's going around once. Once in the positive direction. Okay, or we could say define alpha 2 of t to be 2t. But we should do it mod 1. So 2t at t equals half would be there, and at t equals 1 it would be back, so it's gone around twice. Goes around twice. Okay, well I guess you can see the pattern. You could also define alpha 3t, that's 3t, mod 1. And there's no need to restrict ourselves to positive multiples. We could also talk about alpha minus 1 of t, which is minus t, mod 1, which goes around the opposite direction. Or alpha minus 2, it's another loop, that's minus 2t, mod 1. So the various loops that we're talking about are things like this. So that would be alpha 1. Here's alpha minus 2. Alpha minus 2 would go around once and then twice. So that'd be alpha minus 2. And so on. And then how does the multiplication look like? Well, if we took alpha 1 and we multiplied it by alpha minus 2, then that would be the loop that went around there and then went around twice in the opposite direction. And that would be homotopic. There'd be some slack in that rope. But if we went like this, and then just imagine there's some slack and went around twice, that would be homotopic. If we tightened the rope, we could reduce it to alpha minus 1. And we're really working with the equivalence class or the equivalence type. So that's really what we're interested in. It's not the loops themselves that are interesting, but the homotopic classes of those loops. So in other words, if you take a loop like this and you fiddle around with it a little bit by having a little snag like that, it's still the same loop. It's still equivalent loop or homotopic, because you can deform this continuously back to where it was started. So slack like this can be pulled together. And so the result here is that the group pi of S1 is then just the same as the integers. It's really the same as the integers under addition, because we're just adding these components. So alpha n times alpha m equals alpha n plus m. That's the law that relates the fundamental group to the integers. Integers being these indices here that can range through any positive or negative integer values. Okay, so we've talked about this algebraic object, the fundamental group that we're associating to a surface now, a surface together with a base point. And now there's a main fact. Okay, the main fact is this theorem that pi of m x0 is a group. I mean, I've been calling it a group, but I haven't told you what a group is. But it actually is a group in the mathematical sense under this multiplication star. And so I need to tell you what is a group. Or what does it mean in this case here. Well, a group means that you have a multiplication on a framework of things, and this multiplication should satisfy three different things. The first is that there is a special element, usually called E, such that, or with the property that E times X equals X times E always equals X for any X. And E is called the identity element. So there has to be an identity element. And then the second criterion is that for any X, there is an element usually called X inverse with the property that if you take X times X inverse in either order, you get the identity element that we've just talked about. And that's called inverses. And the third property is the associativity property, that if you have three elements, X, Y, and Z, and you first multiply Y and Z, and then you multiply by X, then that's the same as what you get when you first multiply X together with Y, and then Z on the end. Now the order of things that matters a lot, but okay, this is called associativity. And there's then an additional property which is not one of the parts of the definition, but a group is called commutative if in addition, if X times Y equals Y times X for any X and Y. But the actual rules for a group do not insist that it be commutative, so we're also considering non-commutative groups. And so the main fact here is that this multiplication of loops on a surface is actually a group. And so that's going to be our first order of business for our next lecture, and I'll see you then.